Okay. So yeah, with that, I'd like to introduce our speaker today. It's I guess before we go to the speaker, let's do a quick round of introductions through this list of the participants. I'm gonna try to put this here on a let's see. Okay, maybe if you can all see this, we can go in this order. Are you able to see?
Yep, we can see the order.
Okay, so I'm Sudhir Dulipala. I'm the chair of NCITE SimCap committee this year. Colin, you can go next.
Hi, yeah, I'm Colin Schroeder. I work for SRF. I've been working here for about 4.5 years. I've attended quite a few SimCap meetings in the last few years. So,
Guess I'm next. Eric Trippy. I am with GHD out of the Detroit area. And as Sudhir had said, I'm current chair of the National ITE SimCap Committee. And I don't know if Sudhir may mention this later, but we do, if you are going to be at TRB or would like to call in to a meeting that we have scheduled there on July 11th at 1:30 or 1 o'clock, somewhere around there. I can add you to our email list and send you the invite to that. So, and I guess just quickly, my email address, if you want to email me for that invite, is just my name, eric.trippy@ghd.com. And be happy to send you an invite to our upcoming TRB ITE meeting.
Hey everyone, my name is Jack Olson. I work at Kimley Horn. Been working here about 3.5 years, and I've been involved with SimCap on and off a bit for the last few years. I'm also the outgoing chair of the Younger Member Committee of NCITE and the current membership chair.
Good afternoon. I'm Jerry Kotzmacher with MnDOT. Work for the Central Office Signal Division. I've been there for about 30 plus years, and majority of that time has been in traffic signals.
Hey everyone, Joe DeVore with KLJ. Been here almost or a little over 5 years now, or almost 5 years now. Do a lot of traffic operations and safety.
Hello, I'm Kelsey Rutherford with Bolton and Mink. I've been with Bolton and Mink for about 6 years now. Yeah, I primarily work on traffic corridor studies, do a lot of VSIM and some traffic analysis. So really like being a part of this group.
I'm Mark Powers from SRF. I was last year's chair of the SimCap committee, and this year I was a director of NCITE.
Hi, my name is Matt Colas, Senior Transportation Engineer, and I work with Eric Trippy over at GHD.
Hello, this is Shakwat. I'm pretty much new in the SimCap committee. I just recently started my professional career with WSP. And yeah, that's all about me. Thank you.
Hi everyone, I'm Mike Konzielka with Alliant Engineering. I've been with Alliant for about 1.5 years, previously with Kimley Horn. I am the co-chair this year for the SimCap committee, and I will be chairing next year, starting a couple weeks here.
Hi everyone, I am Praveen Bakal. I work for ISMUS and been there for about 5 years now. And I've been involved with different subcommittees of NCITEs for the last few years. I work in different traffic and transit projects.
I think I can introduce Tom. So Tom is
Sudhir, looks like some Brian has joined also.
sure. Yeah, I think
Just wanted to give him
I
a
saw a
chance.
couple more. So
Right,
anybody
yeah.
else before we go to Tom?
Yeah, and then we can
go
talk
ahead.
about it.
Yeah.
Yeah, I can just speak up. Brian Nemeth with Bolton and Mink, leading the traffic group over at Bolton and Mink for, I don't know, 20 years now. So, but I helped start this group. So I'm glad it's continuing to go along, and I'm just kind of joining in and seeing how everything is.
Thank you, Brian. Adam, did you?
Yep,
wanna
I also joined late. So I'm Adam Capitz, traffic engineer at Stantec, and have been there for 4 years.
Gordon.
Yep, Gordon Parikh at SRF. I'm in the ITS group.
All right. So our speaker today will be Tom Greasy. He's Vice President of Transportation Engineering at Caliper. He's the chair of TRB's Standing Committee on Highway Capacity and Quality of Service. I think he wrote a paper in ITE Journal last January on this topic, and he's here to speak to us today on this topic of intersection capacity analysis. Are you doing it wrong? Anything else you want to add, Tom? Go ahead and let me make you a co-host actually, so that you can start sharing.
I might be already at least.
Okay.
So
let me stop sharing so that you can present, and then.
So do you?
Yep, we see like the PowerPoint.
Okay.
Yeah, and
so
we
you see it?
Yep.
Okay.
Right.
Well, thank you, Sudhir, for having me. Brian Nemeth, you should know this material inside and out. So, so Brian has been a friend and subcommittee member of the Highway Capacity Committee in the past, and so a lot of the stuff that I'm going to say, he's heard me say before. And just a little bit about me. I currently with Caliper Corporation, and we're in the software business, even though we do a lot of consulting work as well. I've been around for a long time, yet it seems like it was just yesterday that I started. 30 of my years have been in consulting. Adam, most recently, I was with Stantec before I left in October of 2018. And my current position is Caliper. I been, doing HCM analyses since the mid 1980s. I've been doing simulation modeling since 2000. And as Sudhir said, the other thing that I do is I chair the TRB Highway Capacity and Quality of Service Committee. So I've got just a little bit longer to do that before I will be rotating out. So yeah, what I wanted to talk about today, and this is the article that was in ITE Journal. It was actually January of 2020, so it's almost 2 years ago. But it's about the topic of oversaturation. What do we do? What do we do wrong when we have situations where the demand is greater than capacity? D over C, that is greater than 1.0. Originally, we used to call it V over C, volume, but there was the whole theoretical argument is that volume can never be more than capacity, so therefore you could never have a V over C greater than 1, so we should call it demand, because capacity is theoretically the maximum flow that you can achieve. So it's now typically referred to as demand to capacity. Going way back to the 1985 Highway Capacity Manual, which was, I actually had a 1965 version of the manual as a class book during my undergraduate work, but never really used it. But I really refer to the 85 version of the manual as the modern HCM. And the methods that were documented in the 85 version of the manual did not do oversaturation. They basically said that warning, you're getting into a zone where the methods break down, so use with caution. And after the 85 manual, the methods in the manual were able to address oversaturation. And since the 2000 version of the manual, guidance on oversaturated conditions and doing analyses within those has been offered, but it's frequently been ignored. With each of the subsequent editions of the HCM, and I say we, the HCM community, the committee, we've been able to, get a stronger awareness of oversaturation and the limitations of the methodology with every edition, but still a lot of misuse. And it's primarily due to misunderstanding by the users and or misapplication of the methods, and simply just using software and not really understanding what the software does or does not do. So this is the article. You can actually look it up. It's the January 2020 edition of the ITE Journal. So this group then dealing with simulation, particularly, well, this entire slide should be familiar to you, but just quickly, the deterministic methods are not subject to randomness. This is what's in the HCM. They're macroscopic, so they deal with flow rate, that is vehicles per hour. No matter how many times you do the analysis, the same inputs are going to give you the same output. And, two of the most prevalent, not the only two, but certainly highway capacity software, HCS, and Synchro are the most commonly used tools. There are some others. Stochastic is, these random variables are incorporated to represent attributes that we don't know with certainty. They behave within predicted ranges. And these are microscopic in that we model individual drivers that are following these rules of the road that just so happen to be defined by mathematical models. Rules for car following, lane changing, gap acceptance, those types of situations. So therefore, we use random number sequences and perform multiple runs because, and we've all done this in collecting data, that we may collect data during a typical day for several days in a row, and yet we're going to get different results every day. So in simulation, we simply do this with multiple runs, and then we accumulate statistics such as a mean, standard deviation, range to quantify the results. There are a number of simulation tools that are out there. The most commonly used, I get to list Transmodeler first because I work for Caliper, and that's our simulator. VisSim and AimSun are also, as you all know, used quite frequently. There's some others. CoreSim is still around. There's Sumo, which is an open source. Paramix, was an early one back from the 1990s. Don't see it as much anymore, but there are a number of commonly used tools that do microsimulation. Looking at the deterministic tools and the deterministic approach that was in the highway capacity manual, most of the procedures in the HCM are based on a peak 15-minute rate of flow, which is then converted to an equivalent hourly flow rate using the peak hour factor. You can see the formula for that's on the right-hand side. A lot of people over the years have just not understood, though, that an HCM analysis is really analysis of the heaviest or the worst 15 minutes during the peak hour, the peak within the peak. And that's what the peak hour factor is for, is to take that worst 15 minutes and equate it as if it were an hourly flow rate. So a peak hour factor range is somewhere between 0.25 and 1.0. You can do the math if you'd like, but the lower a peak hour factor is, the more peaked within the peak the traffic conditions are. But what happens if we have multiple periods when traffic conditions are bad? Maybe they're not all 4 periods within the peak hour, maybe there are 2 or 3. And how might congested traffic conditions in one 15-minute period affect the conditions in the next subsequent period, particularly when we're dealing with oversaturation? This is directly out of the HCM. and it discusses the three different approaches to doing looking at a single period of analysis versus multiple periods. The one on the left, approach A, is really the default approach that the HCM takes, looking at the worst 15 minutes. And so this histogram is the an hour divided into 4 15-minute periods. And we focus really on the worst of those. But because all of the volumes are in an hourly flow rate, we use the peak hour factor to basically make the entire hour the line even with the top of this one bar here. We look at a single analysis period, there's an implicit assumption that the traffic demand does not vary, that it stays constant over that entire hour, which unless we have really heavy traffic flow, we know that that's not the case. And then the third approach is discussed in the HCM is to evaluate each one of these individual 15-minute periods. So let's take a moment and look at the delay equation. So control delay is the service measure for the signalized intersections method in the HCM. The equation for control delay back in the 1985 version of the manual had two terms, a D1 term for uniform delay, D2 for incremental delay. The D1 term is the classic Webster delay diagram that shows the triangle, and the delay is the area under the triangle with the assumption that the arrival demand is uniform. And then the incremental delay is this randomness that gets added to it, plus some additional delay due to cycle failures. We're beginning to at least acknowledge that oversaturation exists, but still is limited. And in fact, that was the caveat to the method, was that it really should be applied for D over C less than 1. And if it was oversaturated, then it just said, beware. It really didn't give you any guidance. Particularly back in 1985, microsimulation was just being discussed, and it was only done on mainframe computers. And we really didn't see anything that had animation to go with it. The progression factor back then in the 85 version of the delay equation, the progression adjustment factor was applied to both of the terms. We had an update in 1994 and then a second one in 1997 that actually added this third term to the delay equation. It also, the progression adjustment factor was moved to be applied only to the first, the uniform delay term. But the D3 term was that residual demand delay to account for oversaturation queues. In other words, not all of the demand gets served. There's some residual queue that gets left over. And that D3 term was added to the delay equation to account for that. That was a kind of a minor update to still the 85 version of the manual. So we had a new version, a new manual in the year 2000, and it provided documents and guidance on extending the procedure over multiple time periods. So now all of a sudden we're talking about doing multiple time period analysis, but a lot of people really didn't understand it. And the software tools really weren't doing it just yet. The guidance in the HCM though, and it's very clear today, if the analysis period's demand volume exceeds capacity, then a multiple time period analysis should be undertaken when the study period includes an initial analysis period with no initial queue, and again, a final period with no residual queue. So you start the analysis before there's a queue, you end it when there is no queue. So you contain the analysis in time so that the oversaturation is contained within your analysis period. This approach provides a more accurate estimate of the delay associated with the congestion. So that is there in print at the bottom of page 19-19 in the current version of the HCM, which is the 6th edition. So why is this important? And I'm going to show you in a minute. For oversaturated conditions, a single period analysis using a peak hour factor will underestimate delay and possibly significantly. Now remember, this is the default approach. This is collect hourly volumes and compute the peak hour factor. But if you don't select, it depends on the software tool that you're using, but if you don't select multi-period, this is going to be the default. I know it's that way in the HCS. And also this is important because it can result in signal timing with shorter cycle lengths and phase times that don't process the actual demand, especially if you're doing an optimization that is delay based. If you are underestimating the delay, then how do you know if you're going to have an optimal cycle length and optimal timing plan? It could also provide problems with inadequate turn bay lengths due to underestimation of queues. So the deterministic methods that are from the HCM and implemented in HCS and Synchro, when you have a oversaturation in a turn lane, it simply raises a red flag, but it doesn't do anything to account for when that queue backs up into the adjacent main through lane. It just puts a red flag up. Well, if you've been doing simulation work, which I assume most if not all of you do quite a bit, you'll see that that actually does make a difference. It affects the flow rate of those through lanes. The deterministic methods don't account for that when that queue spillback goes into the through lanes. And for things like where there's developer impact fees, if they're based on particularly the intersections and delay and level of service, then you may be underestimating what the delay impacts are. They're not fully mitigated, and therefore maybe the collected fees are insufficient. So let me illustrate this, and you can actually do this yourself. This is from chapter 30 in the HCM 6th edition. Chapter 30 is part of volume 4. Everything in volume 4 is online, so you can actually, even if you haven't purchased a manual, volume 4 is accessible. So you can do your internet search and find volume 4. You just register, and then you can have access to the materials there. Go to this chapter and you can recreate this problem yourself. One thing that we did is we took the hourly volumes there and we inflated them by 50% to make sure that we would be oversaturated. And then we just used the highway capacity software to do the analysis. Just want to focus on this eastbound approach and on these two movements, this eastbound left turn and the eastbound through movement. You can see the 2 lanes with 1,500 vehicles per hour are the through movement, a single left turn lane with a demand volume of 300 for the left turn. The difference between the two is that this left turn movement is undersaturated. The through movement is oversaturated for these conditions, which include the signal timing parameters. So let's look at the difference in the results. This is a really busy table, a lot of information here, so I'm going to just take a moment and let you digest it. First of all, the left turn lane is shown in this block right here. I assume that you can see my mouse pointing to it. And then the through lane is on the right-hand side. We have the comparison of a single period analysis in the first column, and then multi-period. So we got a 1 hour with 4 15-minute periods, and these successive periods 1, 2, 3, and 4 are shown going left to right. All right. So hopefully this is clear to everybody. When we look at the eastbound left turn, which is undersaturated, so this first row in the table, it's got a volume to capacity or demand to capacity ratio less than 1. It's close to saturation, but not quite. Using HCS to compute the control delay, and for whatever reason, there's a little bit of rounding difference in the software or something. It's not exactly the same, but it's virtually the same. Well, we're essentially getting the same answer, whether we do a single period with a peak hour factor or do a multi-period because it's undersaturated. Get a different story here for the eastbound through lane, where we have a demand to capacity ratio of about 1.2, 1.3. So the first column is doing it as a single period analysis, and then doing it within HCS as a multi-period analysis. You can see that the differences in the delay values, particularly by the time you get to the end of time period 4, is greatly different than if you only did a single period analysis. 5, 6 times the delay if you do a multi-period. When we look at the initial Q delay, at the beginning of time period 1, we're assuming no initial Q that was unserved from the previous period, so that's a 0. But then, and this is for both lanes, you can see that all of a sudden now this delay component, I'm sorry, this is delay in seconds per vehicle. You can see how this rises. Our actual Q is down here at the bottom. But the point that I want to make is that this was doing a single period analysis with a peak hour factor. This was doing multi-period analysis, starting with the period that was undersaturated, and progressively, as we went through each successive 15-minute period, conditions got worse. So by the end of the 4th period, that average control delay was significantly worse than if we just did it as a single period. So just kind of saying it another way, if you just want to put it graphically, this is for that eastbound through movement. There's a pretty big difference in just doing a single period analysis with a peak hour factor compared to doing it multi-period, doing it properly. The other thing is that you can do even though in HCS, the default is single period, you can do multi-period analysis in HCS. The last time I used Synchro, and I know that Synchro is very popular, and I use Synchro 10, I haven't used 11, it did not do a multi-period analysis. It only did single period. I don't know if that's changed in Synchro 11, but it certainly was not there in 10. And of course, this is the implementation of the HCM methodology. So, you know, they're both software tools, but this kind of illustrates that when you're oversaturation, you get a big difference in single period versus multi-period if you use a deterministic approach. Now, let's look at doing it in micro simulation. Of course, this is because this is SimCap and everybody's familiar with simulation, then, you know, this is familiar stuff for you. You understand that that vehicles enter the network at entry and exit points, and it's depending on the tool, there's a warm-up period that's required to preload the network. And you know, these vehicles waiting to enter the network are kind of stacked invisibly outside. And, you know, in this case, there's an approximation between unserved trips and unserved demand, even though the trip can start near the end of a simulation period and not make it all the way through. And depending on which software tool you use, it may be counted for as you know, an incompleted and therefore an unserved trip. Going back to where vehicles enter and leave the network, as far as entering the network goes, you need to be aware of the software tools differ on what distribution the user can employ to as far as how vehicles enter the network. For simulation projects, we typically have to cut the network somewhere. We can't simulate everything. So wherever your network boundaries are, you need to be careful about what is close by and make sure, to the extent that you can, that the entry of vehicles into the network at that point is not affected by something upstream like a closely spaced intersection. You may need to include that in your analysis and move even farther upstream just so that you can incorporate those arrival impacts correctly in your simulation model. Some simulators will allow you to customize your demand profile so that you can make it mimic what might be in counts, for example, where you might have a peak within the peak. And simulation models also allow you to have an analysis period that's longer than an hour. So when we get into metropolitan areas, we typically have, you know, a peak period of 2 or 3 or even 4 hours, depending on which metropolitan area you're in. So be aware of that, and just make sure whatever tool that you use, make sure that you're aware of your ability to customize your demand to be truly reflective of what is kind of out there on the street. Of course, the model calibration and validation are extremely important. Again, both in time and in space, we need to get beyond the oversaturated regimes in the beginning and the end, so that you can accurately capture the effects of oversaturation. And remember that there's a difference between traffic demand and traffic counts. And I've got just something real quick here in a minute to illustrate that. But I think we've, within the profession, we've done a better job of calling it out now, that when you're oversaturated and you are doing intersection counts, you're not measuring demand, you're basically counting saturation flow rate. So other means must be taken to get an accurate estimate of travel demand. And in calibrating your model, things like queue lengths and travel speeds are all affected as well. Using microsimulation software, be aware of the differences between the headway buffer that's used, which is akin to the saturation flow rate that you're going to have in the deterministic tools like HCS and Synchro. Big thing is when you have actuated signals. And, I had to confess that it took me a while to finally understand this. So when you're using deterministic software and you have actuated control, and you are entering parameters like a minimum green and a maximum green, the HCM method is simply, it has a model in there, a phase duration model, which estimates based on the demand in these other geometry, these other conditions, over your analysis period, what the average phase would be. So you may have a side street phase with a minimum green of 15 seconds and a maximum of 30, but it may vary from one phase to the next, and it may average out at 24 seconds or whatever. So that's actually what goes into the equation for capacity, where it's your G/C ratio times saturation flow. So the deterministic tools have a phase duration model, which takes that actuated signal and approximates it as though it were pre-timed. You need to just understand what's going on with that. And then just briefly, I talked about demand versus counts. You can construct this is just a simple queuing analysis where the demand from one time period, is the departures plus those that are in the queue, minus what were in the queue from the previous time period. And just kind of illustrates, when you put this in a graphic form, that while the demand may increase at some point, you want to make sure that you can incorporate your analysis to include this entire profile, so that there are some parts of it where when the demand is greater than capacity, they're going to continue to stack up. At some point, the demand will be less, but you'll still have a residual queue built over. So this kind of illustrates that if you are counting at the stop line, you're going to, from one 15-minute period to the next, when you're over capacity, you're going to get similar numbers until you finally get out to the point where you're getting rid of this residual queue that's backed up. So again, just points to remember on that. This is a good illustration of when your conditions are oversaturated and where your stop line counts don't equal the demand. So it may be necessary to move upstream in the back of your queue and provide a second count location. It's important at the stop bar, you do need the distribution of turning movements. So it's important to do that, but you may need to come upstream at a second location. Now I know that we were providing some guidance. We actually helped author a manual that was implemented by the Ohio Department of Transportation. And it was both on using simulation and on using HCM methods as implemented through HCS. And we had a whole lot of discussion about traffic counts over multiple time periods, 15-minute periods, but for multiple hours, and upstream count locations, and what, doing it the right way. I would just say that there was a lot of discussion about concern about driving up the cost of a project with data collection. And I understand that, I certainly do. But, the other side of the issue is, the other question is, it's important to get it right. Do you want to, want to know the right answer? So, maybe you've had some similar discussions with clients in your region, but a lot of debate about that. So again, particularly where you have an approach that's oversaturated, it's always a good plan to go upstream from that, away from the end of the queue, to get a second count, and maybe using that adjust what happens at the stop bar. Excuse me. In simulation, my experience as a practitioner has been, depending on the software tool that you allow, if you can use an origin destination matrix, it's usually better for dealing with oversaturated demand than if you use intersection turning movement counts. Our software will allow you to do both, even in a multi-period format. Given one versus the other, I think OD matrices are a little better. I won't get into the details of why, but there's more flexibility, and particularly as a practitioner, when you are considering maybe looking at some design alternatives, it's easier to, a lot of times it's easier to maintain your quantified demand in an OD matrix. And even if you are undersaturated, particularly if you're getting close to saturation, using a deterministic analysis, it's never a bad idea to do a multi-period analysis. Maybe you want to do an initial check to see how close to capacity you are. Of course, as practitioners, most of the time we wouldn't be doing a study unless we were getting close to capacity, if not over. So something to consider. But particularly, let's say that you're using HCS, it's just a little bit more effort to set it up. But in the end, HCS will automatically compute that incremental demand as part of the D3 term of the delay equation. So there's a good reason for doing it that way. Final thoughts. Tools are just that, they're tools. As the analyst, you're responsible for applying them properly and coming up with the right answer. But select the right tools for the right reason. I've heard, because it's easy to use, way too many times, to the point that it's sometimes been really frustrating to me, because people are selecting them and maybe using them and getting the wrong answer. Know how your tools behave, particularly the assumptions that go into their use and their limitations. All analytical methods have assumptions and limitations. All software tools have assumptions and limitations. Know what they are. And remember that decisions on how an agency is going to spend millions of dollars on infrastructure improvements might be riding on your analysis. So don't take it for granted. Some very important decisions are going to be made, and please keep that in mind. So with that, there is my contact information. I'm going to leave it up there for just a second. And trying to figure out how to unshare it. All right, here we go. So I'm going to stop sharing and open it up for questions.
I'll maybe start out the questions, Tom. We've been doing a lot of kind of daily analysis, looking at trends throughout the day at intersections, not necessarily just the peak hour, to look at intersection benefits throughout the day, even if maybe the peak hour is a little worse for that preferred alternative. But we've been implementing kind of using a similar process to putting in 15-minute volume periods to capture that peak hour factor, but really looking at just the kind of average of those hourly results. Would you say that's a good process to use when you're kind of considering that peak hours to look at the average of, you know, the hour for that versus just the 15 minutes?
So I'm not totally, I think I follow what you're saying, Joe. I'm not totally sure. It's never a bad idea. I think it's always good practice to look at smaller time slices and see what's happening from one to the next. But if you get more analytical than just looking at maybe a distribution of your demand, and you actually do an operational analysis and you know, where you're estimating delay and level of service or queue lengths or whatever, then I just want to make sure that everybody's aware that using maybe some of the traditional approaches with, well, the traditional approach with a single period analysis with a peak hour factor is you're gonna be nowhere in the ballpark of what the actual delay is if you're over capacity. So it's kind of a user beware thing. It just puts the proof to what's been in the manual really since 2000. Okay. Now, there are other things, and particularly when we're talking about screening, looking at trends and that go beyond your traditional intersection analysis. So, you know, we can justify, we've all done this, justify maybe looking at this or that, like I said, it is a screening or whatever. But when you get to the operational level of analysis, it's just important that you understand, that we all understand, it's a game changer when we reach that point of saturation. In fact, back in the graduate level traffic engineering courses that I was taught, and there was shown a curve, you know, over time moving from left to right, and it was kind of upward curved, and when you reach, and it was typically delay versus V over C, and when you hit close to 1.0, it really went vertical. You know, it increased sharply. It was relatively flat, but boy, when you got close to saturation, then delay increased exponentially. And that was kind of the, you know, the preface, if you will, to these methods don't deal with oversaturation very well. Now, we've done a whole lot in the profession since then, and obviously the tools are better.
I have a question, I
Mhm.
guess, related to simulation. Would you recommend using 15-minute level volumes in simulations, or is it okay to use an hourly volume, assuming that the model takes care of because of the stochastic nature, it takes care of creating the internal peaks itself?
Yeah, here's the thing. I think it's, and I've done this, we've all done this. I think it's really important to look at your demand that you have quantified in your simulation model, and particularly compare that to counts. That's why I think it's so important to find some mid-block count locations that are away from the impacts of the backup queue, and really look and see, does that over the course of your peak hour, peak 90 minutes, peak 2 hours, is it fairly consistent, or does it vary? You know, a lot of times you'll see maybe a couple of peaks within a peak, I don't know, 180 minute peak period. So the better that you can use your tool to approximate what's out there in the field, I think it's, the more you can do that, the better. So even in simulation, if you just put in, let's just say your simulation period is an hour. If you just put an hourly flow, your model is going to assume that the demand doesn't vary from 1 minute or 1 second to the next. The distribution of that may change, but the demand is going to be roughly the same. In fact, if you run multiple times, you're going to get, you know, a pretty tight average on that. But the reality might be that you have a very pronounced peak within the peak. And some of these things like queue spillback from turn lane overflow could become much more significant at certain points of the simulation. So I would recommend adjusting your demand profile to fit actual count data when and where your tool allows you to do it whenever possible. It's an extra step, but it's certainly it's a more accurate step, and it's not going to hurt anything. Worst it's going to do is cost you a little bit more effort and time, but it's going to give you a lot better answer.
Any other questions? All right. So I'd like to thank Tom for his presentation today. It was very informative.
Thank you all. What I will do, I'm not going to stay for the rest of your meeting, but Sudhir, what I will do is I will email you a PDF of this in case anybody wants a copy. You can distribute it from there.
Yeah, Mike will be able to post it on the SimCap committee website.
Okay, so yeah.
Yeah, and then I can actually stop recording here.